Next, let's look at situations where 5 things are attached to the central atom. All right, so this is a little harder to see. So it's called trigonal bipyramidal because you have a triangle base, which you see here, or the equatorial plane is what it's called. So it looks like a triangle, okay? But then you have a point on each part. So this triangle forms a point. So you have one triangle here, and you have one pyramid here with a triangle base. So that's where the name trigonal bipyramidal comes from, because you've got bi, 2 pyramids with a triangle base, trigonal bipyramidal. And so each of these has a different shape, which is kind of fun to look at. But when we're doing this, picture these 3 entities here, this equatorial plane. They're all in the same plane, so they're all like within the same level, or like a piece of paper. And then coming up out of the paper, you have one carbon or one atom, excuse me, whatever it is, coming up, and one that's coming down. And so this is where you get this fun trigonal bipyramidal shape that you see here. Let's look at each one a little bit closer. How about we start by drawing the Lewis structure for phosphorus pentachloride. So phosphorus has a total of 5 valence electrons. Chlorine has 7 times 5 is 35. So we need to draw a total of 40 valence electrons on this structure. So we've got phosphorus with 5 chlorines coming off of it. And normally I just kind of draw it all willy-nilly like this. But can you see how there's 1, 2, 3, 4, 5 structures coming off of it? All right, I've added my 6 electrons around each of my chlorines, but now you can see that there is a central atom, phosphorus, with 5 atoms or 5 things coming off the outside. So my electronic geometry is trigonal bipyramidal, but my molecular geometry is the exact same. And so my shape is going to look like this, where these 3 of my chlorines are all in the same plane, and I have 1 chlorine above the plane and 1 chlorine below the plane. Orienting it in this direction is going to make it so my electron density is as balanced as it possibly can be. My next one to look at is a seesaw. I kind of like this one. So you're going to remove one of these atoms that you see here, and you're going to replace it with an electron group. And so if you kind of see, so you kind of look from this figure to this figure, see how now if we remove this atom here and then rotate it 90 degrees, it looks like this, where this is your fulcrum point. Okay, so this is the thing that's holding up the seesaw, and then now you have your seesaw on top, and you've got your little children playing like you see right here. Okay, so that's why this is called a seesaw, is because it looks like a seesaw if you're only looking at the atoms that make up the structure. So you may be thinking, what has this cool, crazy shape? Let's try tellurium pentafluoride. So tellurium has 6 valence electrons. Fluorine has 7 valence electrons times 4. So 7 times 4 is 28, plus 6 is going to be 34 electrons. Tellurium goes in the middle with fluorines on 4 sides. Fill in all my valence electrons. And then count them. How many do I have? 8, 8, 8, and 8 makes 32 electrons. So I need to draw 2 more valence electrons coming off of tellurium. And so here you can see how that's my lone pair in my structure. And so all the fluorines form the seesaw picture that you see here. So if I ask you, what is the electronic geometry for tellurium pentafluoride? You would say trigonal bipyramidal. What's the molecular geometry? It is seesaw. Let's do something that is T-shaped now. Can you see how if you remove 2 atoms, you're going to have this is kind of linear, and then you're going to have one that comes up off the T. Okay, so the line part, this linear part, is your axial plane, and then you've got one that comes straight off in that equatorial plane. Either way, it looks like a T, so that's why it's called T-shape. Let's do bromine trifluoride together. Bromine and fluorine both have 7 valence electrons, so 7 times 4 is going to give us 28 electrons to put around my Lewis structure. Bromine's going to be in the middle, fluorine around it. Add in your electrons. Count up your electrons. 8 times 3 is going to give me 24, which means I need 2 more lone pairs on my bromine. And it looks exactly like this figure here, where you have 2 electron pairs coming off that central atom and 3 electron dense atom groups coming off of the bromine. So your fluorines are all right here. Your central atom is the bromine, and you have your 2 electron groups, which means the electronic geometry is trigonal bipyramidal and your molecular geometry is T-shaped. Next, let's look at our iodine ion, I3-. So you've got iodine that's connected in a row, and then you have electrons all around the iodines. Let's count up how many electrons we've drawn so far. We have 8 and 8 is 16, 17, 18. How many do I need? Iodine has a total of 7 electrons, times 3 is 21, plus we have an extra electron from the negative charge. So we need to draw our brackets around it, put that negative charge in there, and then like I said before, we had 16, 17, 18, so we need to draw 2 more, 19, 20, 21, 22, which means I have 3 electron pairs around the central atom. All of those are in the equatorial plane, and then here in a line in my axial plane, now I have my 3 iodine molecules. So it is trigonal bipyramidal, and it's linear as far as molecular geometry goes. The number one way I see students messing this up is that molecular geometry refers to the atoms or the entities, not the electron pairs. So they'll often name this one as trigonal bipyramidal and then electronic geometry linear. It's opposite. Molecular is linear because you're only looking at the atoms in space. Ignore the electron dense regions of the electron pairs. Next, let's look at valence shell electron pair repulsions for when we have 6 things attached to the central atom. Now we're only going to look at 3 classifications of that where we have 0, 1, and 2, but I bet you can imagine what the other ones are called, meaning if you've only got 3 of them, T, 2 of them, linear, but we're just going to look at these 3 examples for right now. Electronic geometry of octahedral, because it looks like an octahedron. My molecular geometry can be called octahedral, once again, same as the electronic geometry, square pyramidal, or square planar. Now where does it get these names? Square pyramidal, it's literally a pyramid with a base of a square, but a pyramid because it all comes to a point. Whereas square planar is a square that's all in the same plane. So these names make sense based on the groups that they're describing. Let's look at an example of the first one. So sulfur hexafluoride. So notice here we've got our octahedral shown where all of my little points are coming together, and then, opposite here. It's kind of hard to draw it, okay, but you can see it right here. So sulfur hexafluoride, SF6, it's got this octahedral shape. Next, let's do an example of something that is square pyramidal and octahedral. So we've got antimony pentachloride ion, so SbCl5 with a 2 negative charge. Antimony is below nitrogen with 5 valence electrons. Chlorine has 7 times 5 gives me 35 plus 5 is 40, but we have 2 extra electrons from my charge for a total of 42 electrons I need to draw. So now let's draw it with antimony connected to 5 chlorines, and then draw all those wonderful valence electrons around your chlorines. And then after you've done that, that's going to be 40 electrons because you have 8 times 5 is 40. So you have 2 electrons remaining to put around that central atom. And so that's the electrons you see here. So now they have this square base with a pyramid coming up all out of it. So it is octahedral because it still forms an octahedron if you include the electrons. But if you ignore the electrons, it looks like a square pyramid. Last but not least, we have xenon tetrafluoride. Xenon has 8 electrons, fluorine has 7 times 4. 7 times 4 is 28, plus 8 is 36 electrons. And so for this one, you have xenon in the middle, fluorine all around it. You add in your electron pairs on your fluorines, and that's going to give us a total of 8 times 4 equals 32. So we need 2 more electron pairs around the xenon. And so now you can see you've drawn those groups. So therefore there are a total of 4 things around. So now there are a total of 1, 2, 3, 4, 5, 6 things, if you will, around the central atom, which means it's octahedral. But 2 of those things are electrons, which means it's square planar because those fluorines are all going to be in the same plane, and one of these electron groups is going to be higher than the central atom and one is going to be lower. And so that's why it's called square planar, but the electronic geometry is octahedral. So remember, just kind of summary here, what we're saying is that you can use the Lewis structure and those bonding and non-bonding pairs to predict what the shape of all of these structures are in a 3D area or in real life.